Good morning, students. In the previous classes, we have studied various aspects of electrostatics. Especially, we studied about capacitors and various combination of capacitors, and also we studied how there is dissipation of energy when capacitors are connected in parallel combination. Today, we are going to study about how a conductor behaves in an electric field, how a dielectric material behaves in an electric field. You know charging by induction and charging by conduction. What is the meaning of charging by induction? What is the meaning? If an uncharged conductor is placed near to a charged body, what will happen? Opposite charges will be developed on its surface without any contact. This is called charging by induction. Now suppose you are keeping a conductor, for example a metallic piece, in a uniform electric field. Can you give an example of uniform electric field? Uniform electric field. Where is uniform electric field? In between the plates of a charged capacitor. How much electric field is there in between the plates of a charged capacitor? You know how much? Sigma by epsilon naught. This is the electric field in between the plates of a charged capacitor. Charged capacitor means one of the plate is positively charged, then the other will be negatively charged if it is earth. This is your capacitor. In this situation, electric field between the plates is sigma by epsilon naught. Now you are introducing a metallic slab in between the plates of the capacitor. Now what is going to happen? That is a question. You know this idea. If a uncharged conductor is placed near to a charge, then there will be charging by induction. Now you can see the same thing that is going to happen here. Here it is very clear that you kept an uncharged metallic conductor near to the positive charge as well as near to the negative charge on the right side. So you can see induction. So induction means if 1, 2, 3, 4, 5 positive charges here, so there will be 5 negative charges on the other side. And on the other side what is happening? 5 plus. Now, listen carefully. This is your capacitor. What is the direction of electric field? Is it from positive charge to negative charge or from negative charge to positive charge? What is the direction? It is from positive charge to negative charge. So, there is an electric field E naught which is sigma by epsilon naught that is acting from positive plate to negative plate. Is it right? Now, if you introduce this metallic slab, you can see same number of positive charge here and same amount of negative charges here also. So there is again an opposite electric field from the positive side of the metallic slab to the negative side of the metallic slab, and that is also E naught. And you know the value of E naught is sigma by epsilon naught again. So what you can see now? Two phenomena are happening. Now number one, there is charging by induction, and due to that induction you can see two electric field. One electric field E naught towards right side, another electric field which is equal in magnitude but direction is opposite towards left side. Now how much electric field is there? Resultant electric field inside the conductor. Can you tell the answer now? Because inside the conductor you can see there is a field towards right side and there is an electric field, same electric field towards the left side. So the net electric field inside the conductor is 0. So what is your conclusion? If a conductor is placed in an electric field, how much electric field is there inside the conductor? It is 0 electric field. Now see this diagram on the side. You can see that there is some empty space on the left side as well as on the right side. How much electric field is on this gap? Is it 0? Is it 0? It's not 0. The electric field in this gap is your applied electric field E naught itself. And on the right side gap, how much electric field is there? That is also from plus to minus, and that is also E naught itself. Suppose the distance between the plates of the capacitor is D and thickness of this metallic slab is T. Now you can summarize what has happened here. Electric field and corresponding thickness. Electric field E naught is equal to sigma by epsilon naught. What is the thickness of this pillar? How much thickness this is acting? Is it D or T or D minus T? Can you tell the answer? How much space, how much region E naught is equal to sigma by epsilon naught is acting? It is very clear from the diagram. It is from the left side gap and right side gap. Left side gap and right side gap together, the thickness is, how much thickness? It is D minus T. And for this thickness of the slab T, how much electric field is there? Your electric field is 0. So what is the summary? If a conductor is placed in an electric field, how much electric field is there inside the conductor? There is 0 electric field inside this conductor. This idea can be used to explain electrostatic shielding. Shielding means protecting. So you can protect the sophisticated instruments, devices from strong external electric field. How it is possible? For that, you consider a metal cavity. Metal cavity means there is a solid metal piece is given. You can drill out a hole inside it. There is a hole. This is a metal cavity. And this is closed. Now, if you keep this metal cavity in an external electric field, suppose the same idea, you are keeping between the positive plate and negative plate of a capacitor. Is there an electric field inside this cavity? How much electric field is there inside the cavity? It is, how much? It is 0. Why this is 0? Because this diagram and this diagram are very similar. You are keeping a conductor inside an electric field, then the net electric field inside the conductor is 0. The same thing is happening here. So the net electric field inside this metal cavity is 0. If you keep any sophisticated device inside this metal cavity, that will be protected from external electric field. And that idea is called electrostatic shielding. Or we are using the term Faraday's cage for the same concept, for this metal cavity in which the electric field is 0. Meaning this is behaving as a cage where electric field is not there. So you can protect the devices from external electric field. Now one more question. Suppose you are going to a hill station and there is thunder and lightning and you are traveling in a car. Where you have to seek the shelter? Two options are given. One is below a tall tree. Second one, inside the car. Which option you will prefer? Will you sit inside the car or will you stand in the shade of this tree? Which one you prefer? There is very strong lightning. That is lightning, you know, that is a strong electric discharge between cloud and earth. So if you are standing outside on the road, definitely you will get shock because of the strong electric discharge. So there are two shelters for you. One is below the tree and another one is inside your car itself. But one thing, you have to keep the windows and doors closed. Don't sit inside an open car. It's a closed car. If there is lightning, what is happening in both these situations? If the lightning strikes on this tree, what will happen? What will happen? Tree, you know, it is the conductor. So there will be charge flow through this tree to earth. So you are standing near to the tree. So definitely you will get strong electric shock. But if you are sitting inside the car, what will happen? Even though there will be strong electric discharge. What is the speciality of the tire of the car, tire of the aeroplane, etc.? They are not 100% insulator. Little conductivity is there. Whatever charge is developed or distributed over the surface of this car, that will be flowing to earth. Earthing effect that will be produced in the second case. So you are 100% safe inside the car. Or this car is protecting you from the external field or shielding you from the external field. So you are getting the same effect of electrostatic shielding in this case because this car is a hollow conductor. You know sigma, lambda, sigma, rho. Whatever charge is provided, that will be distributed uniformly over the surface area only. No charge will be flowing inside the car. So you are 100% safe inside the car. But this case, you are not at all safe. So the second option is the correct option. So we can summarize the behavior of conductor in an electric field like this. First one, already we discussed, there is no electric field inside the conductor. Inside the conductor, electric field is, net electric field is 0. If electric field is 0, how much charge is there? From the diagram it is very clear. The charge will be distributed over the surface of the conductor only. So how much charge is there inside the conductor? No charge. 0 charge is there inside. If the charge is 0, you can see that your electric field is also 0. There is no net charge inside the conductor and electric field inside is also 0. That is the first one. And the second point, just outside the conductor, you know the electric field lines that is normal to the surface of the conductor. So electric field line and electric field, they are perpendicular to the surface of the conductor. Electric field and electric field line both are perpendicular to the surface of the conductor just outside. Then electric potential, electric field, you know, that is E naught. And what is the value of that E naught? That is sigma by epsilon naught. So electric field on the surface of the conductor is a constant and that value of that electric field is sigma by epsilon naught. If electric field is 0, the surface of a conductor is equipotential surface. What is the reason? Because potential on the surface is constant. Because E is equal to dV by dr, you know. The surface of the conductor is an equipotential surface because on the surface of the conductor potential is constant and electric field on the surface is E naught, that is sigma by epsilon 0. Electric potential is dashed throughout the volume. Can you tell the answer? Electric potential is dashed throughout the volume because inside the conductor or throughout the volume electric field is 0. Electric field is 0 means dV by dr is equal to 0. So how much V is there? V is constant. So there is constant electric potential throughout the volume of the conductor. If you know potential is constant, then work done to displace any charge from between any 2 points inside the conductor, WAB, work done in moving a charge from A to B. That is WAB. What is the answer of this? The answer is 0. Because you know, if potentials are constant, the work done is 0 because potential difference is equal to work upon charge. So here VA and VB, they are equal. Therefore WAB is equal to 0. These are the main 5 points about the behavior of conductor in an electric field.